So today's video, we're going to finally mix it up and try lithium titanate batteries again. Previously, we talked about their long charge cycle life of 20,000 cycles, about how you can charge and discharge them at negative 30 degrees Celsius, and they have all sorts of other interesting features like the C rate. You can discharge at a 10 C rate and charge at a 5 C rate. So these batteries are absolutely phenomenal in quite a few ways, but this chemistry comes with some downsides. First of all, it is not very efficient. So the round trip efficiency, or how much power you put in and then take out, is around 80 to 90%, and I did not like that for solar. That means that I have to buy more solar panels if I wish to use this chemistry. The next problem is that these batteries are very heavy and very large compared to other lithium-ion chemistry variants. Also, the nominal battery voltage is very low, and this does increase the safety of this chemistry, but it's at the expense of having to add all of these cells. You need a 6S battery pack to run 12-volt appliances. And we finally have a 6S BMS. And I previously complained because everything on the market 6 months ago was 5S for BMS for lithium titanate. But after we complained about it, they finally made a 6S DALI BMS. And what's interesting is that this BMS does not have a low temp cutoff, but because this is lithium titanate and we can cycle at very low temperatures, all you need is this BMS and you are done. If you need a battery that can be charged and discharged in freezing cold environments, even like negative 20 or negative 10 degrees at fast rates, you could do it all day long with an off-the-shelf BMS. It doesn't have to be fancy. And some other interesting information about this chemistry that I read online is that people have done capacity tests after discharging these cells to 0 volts. If you do that with any other lithium-ion battery, typically you're going to have degradation and capacity loss, and you can actually see it in the next cycle test. But for these, people have gotten 99 to 100% capacity after discharging them down to 0 volts. So a very strange chemistry. So there's lots of pros and cons. A lot of people have been asking about it, so we're going to throw these cells together. So check this out. These are the cells that we originally tested, and even though it says 40 amp hours, I only got like around 30 amp hours, and that was at a pretty low C rate. So I'm pretty sure that these are repackaged grade B cells because I bought them off of AliExpress. Next, we have these tiny prismatic lithium titanate cells. These are new and they are rated for 20 amp hours. Look how tiny this is. This is actually very new to see such a small form factor battery. There are downsides of prismatics, obviously, for heat transfer, and also if you have an inefficient battery and you have all of that heat generated, this is not going to be a great idea. But if you're using it for solar or something, or you want a small lightweight pack, having these cylindrical cells is just too heavy and too large. So it will be very cool to see how well these do. I want to capacity test these though because they look like grade B. Like, look at this. They put the new sticker on top, the same tape as the last grade B cells. So these might be complete junk. Next, we have from battery hookup, Toshiba Lithium Titanate cells. So we're going to take this box apart, and these are used cells that have been cycled a lot. But because it's lithium titanate, whether it's used or not does not really matter. We should be able to get full capacity from them. But we're going to find out. So we're going to take all of these cells apart and then add this BMS that's for 6 cells and then see what capacity we get. So we have grade B cells, and used cells. And we do not have new cells because they cost so much money. Like, if you want Yinglong cells, you have to do a group buy, usually with the audio guys, and then it comes in a huge crate and then you divvy them up, and I can't afford to do that. And I really don't care that much about these for solar, so I just want to experiment with the cheaper options because, I mean, come on, look how small this battery is. And if somebody is actually using lithium titanate for solar, I doubt that they're going to be using it for a big system, because I think a lot of the specific applications for lithium titanate are with cold weather charging and discharging. So I think that they're going to make small packs with a small solar panel for a specific application. I do not see somebody putting lots of cylindrical cells together for a solar power system. That would just blow my mind. That would mean that they are extremely wealthy and that they don't care about the weight and cost and efficiency savings. So yeah, that just seems nuts. So we're just going to experiment with these tiny ones and build some batteries. And the first pack I want to build is this one. Look how tiny these cells are. And I'm thinking these are grade B cells because look at that terminal, you guys. That is not a new terminal at all. And what I don't understand is if these are 20 amp hour cells, what's the grade A equivalent? Do they actually have a 25 amp hour cell that's this small? Because that would be really incredible. That means that the manufacturing processes are improving right now for this chemistry. It's really hard to find information about lithium titanate though. Even the charge and discharge curve was very hard for me to find. And these were bought off of AliExpress for super cheap. And I just realized that when I bought these, the advertisement showed pink cells, but they gave me blue ones. All right, guys, moment of truth. Here is the voltage. We've got 2.6 volts, 2.6, 2.6, 2.6, 2.6, 2.6. That's a good sign. Sometimes on the grade B cells, if they're all crazy voltages, it's mean that they did not capacity test them. So there's a chance that they actually capacity tested these, but we're gonna find out when we do the test. Oh, look at how tiny these are. Oh, this is interesting. They actually give you a battery terminal stud, which is what they should be doing already for other batteries. And it actually fits on an Allen key wrench. Now that the studs are in place, we need to arrange these in a series configuration for a 6S battery. Guys, these bus bars are very small. I don't know how you could push 10C through this. Are these actually aluminum? Guys, these are aluminum bus bars. I tried scratching it and there is no copper under the surface. And unfortunately, it's actually missing one of the bus bars. I was almost able to triple up all of these bus bars, but it was missing one, so what a bummer. And there is no way that these bus bars even doubled up or even tripled up could push 10C, because 10C for 20 amps, that's gonna be 200 amps. So that's what these cells can push, but there is no way you're gonna push it through this little tiny terminal with these tiny little bus bars. Look how tiny they are. So yeah, I would not buy these for a project unless you are specifically using them for a small system. This is not for heavy load application. Oops, god damn it. So we're gonna do some good old-fashioned electrical tape and put these into packs of 2. And what's absolutely nuts about this chemistry is that these cells can last longer than I'll be alive on this earth. And how cool is that, guys? We have a lithium titanate battery. Now let's check the voltage. We have 15.7, 15.6 volts. Now the balance lead is completed and we're gonna add it to the battery. But a problem is we're at 15.8 volts, you guys. If we connect 12 volt appliances to this battery, we could hurt them. So we're gonna have to bleed off some of that power, and this is one of the problems of working with lithium titanate with standard 12 or 24 volt equipment. The voltage charge and discharge curve doesn't work that well. So we need to drop the voltage and lose some of the capacity, unfortunately, so that we do not burn out our 12 volt appliances when we do the capacity test. Guys, this is a size 6mm bolt for these terminal screws. These are so tiny. I honestly do not like tiny studs, you guys. Compared to these ones, look at this. These are double the capacity, but look how large this thing is. It's like 10 times the size. We just need to add the balance lead, and we have a 12 volt battery. And by the way, this is a 100 amp charging and discharging common port BMS. So for this size battery bank, we can charge and discharge at a 5C rate. But that's if these cells test for that capacity, which we're gonna find out soon enough. So this is not the best way to do it, but we're gonna have a fast load with a cheap inverter and see what happens. It's working! And you do not want to try that at home. The better method is to calculate what size resistor in ohms and then discharge it that way, but this will work. So I successfully discharged to 13.8 volts, and now we're charging up to 14.9 volts for the capacity test. Anything more than that, most 12 volt appliances will degrade. The balance current is 40 milliamps, but it doesn't tell you at what voltage per cell the balancing actually occurs at. So I have no idea if these cells are being balanced because it's not even on the data sheet. So we're almost charged to 15 volts, and once the current drops to 0, then it will be fully charged. So the battery is fully charged, and we're gonna do a capacity test. Guys, we're pushing 96, 100 amps, 97, 100. It's actually pulling the load. That is actually incredible. That's insane. This test should be done in a couple minutes because it's pulling so much power. And this is a 5C rate, so we're not gonna get the full capacity, but I just wanna see what it will do. And the cells are at 50 degrees Celsius. I'm gonna lower the amperage draw for a little while to get a little bit more capacity. So we got 17 amp hours. That's really good at that rate, you guys. That's incredible. So we got 86% of the rated capacity, and the discharge efficiency is 85%. So this is pretty spot on. These cells are the rated capacity. That is so cool. My number was off by like 1%. But these cells are like 48 to 57 degrees Celsius. They are super hot. So are these tiny bus bars, but it actually did it. It actually pulled the load. That is so crazy that these actually worked. Wow. These were pretty cheap, so I wasn't expecting that at all. And we're doing 40 amps. So this is a 2C charge rate. For the next test, I gave it an over voltage situation to charge these cells all the way up to the tip top. And we're at 16.4 volts. So in the last test, I was just trying to satisfy the needs of 12 volt equipment. But for this one, I just want to see what the true capacity is, because it says 20 amp hours for each cell. So we're going to calculate how many amp hours we can get. So we're going to use a 6 ohm resistor to pull 2.9 amps until this battery draws down low enough for the inverters to turn on. We just had to bleed off a little bit of power. The curve at the top of the charge curve is very steep, so it just takes a little bit to drop it down to a good voltage to use with the inverter. $20 amp hours, it actually pulled it off. That means that all of these cells produced at least 20 amp hours each, which is really good. These are way better than these other grade B cells I tested previously. So to be honest, I thought that these were going to perform very poorly, but I am extremely surprised. These are super cheap off of AliExpress. So if you're trying to make a microsystem that can handle any temperature, you should get these. But I also must say they were very hot when we did the test, so you want to be able to space out the cells because they're prismatic. So on these cylindrical cells, you have a lot more airflow, convective flow. And so if you're trying to use this for high C rate applications, this is not a good pack design right here. What's really cool though is that you could use this as a starting battery for a vehicle instead of a flooded lead acid. Because if you think about the C rate and temperature range, and the fact that you only need just a millisecond to start the starter motor of an internal combustion engine, the lithium titanate battery should be able to handle it. The only thing that will mess it up is this BMS. But the cool thing is because the voltage is so high on these, and because you just need something to like almost float charge, so to speak, in an internal combustion vehicle, what you could do is take the BMS off and run it straight from the cells. And I actually have a Prius that we could test this on. So I'm going to figure out what the max amp load is for starting my Prius, and we can try to swap this out for a sealed lead acid. But yeah, very impressive little pack, you guys. This is making me reconsider lithium titanate. Like I said, there are disadvantages, but this is really good for the price. I am thoroughly impressed. The last grade B cell that looked like this performed very poorly. So yeah, I am completely surprised right now. So now we're going to take this battery apart and make another battery. But I did hear of a horror story from one of my viewers. He made a battery pack with the small terminals I was complaining about, and he stripped it out and he had to helicoil it. So, you know, you got to be very careful with this stuff, you guys. And the problem with using this as a starter battery is look at how small these terminals are. If you're using cylindrical, you could totally do it, but look how large this thing is. It will work, but it'll be just as large as a lead acid, but cost a lot more money. So I don't know if that's a good idea. But with lithium titanate as a starting battery, it would last for years and years and years. Now for the next one, these are used batteries, and I need to open up this case to get to them. Pry this cover off. Oh, there we go. I thought that was going to be a lot harder, actually. So this is a used lithium titanate battery from Japan by Toshiba. It has a total capacity of 416 watt hours. The nominal voltage is 23 volts, and it has 19 amp hours and 416 watt hours. And you guys can notice that it has the same pressure expansion valve as the other battery that we just tested. So these might actually be very similar. Oh, look at that. It looks like the same terminal on the top too. Guys, we actually have voltage 2.1. 2.1, 2.1, these are all at 2.1, you guys. That's great. I know used batteries are cheaper, but man, I just hate doing this kind of stuff. I'd rather just throw a battery together in a couple minutes. Guys, I don't think the bottom half comes off because I cut every tab along the side and it will not move. Yeah, that just seems like a bad idea, you guys. I'm just gonna leave it like this then. What's difficult is if I can't open up this pack and access the cells directly, and also these are like spot welded to these bars. So it just makes it very difficult to use this pack. But they are in series, so let's try to find a way that we could tap like 12 or 24 volts off of here. So here's 17 volts. Here's 13 volts. It should be this one. So 21 volts right there. So if you charged it up all the way, you would get 23 volts. So we have this terminal, and this terminal is our main positive and negative. So I think the first step in testing out this pack is we should charge it up. So I'm going to add my 30 volt power supply and see what it charges up to. We're pushing 23 volts at 10 amps. And this is a 19 amp hour battery, so it shouldn't take that long to fully charge. So I want to use this with a 24 volt inverter and charger, but I'm not going to have that much capacity because think about our previous test with 5 cells in series. You're just not going to get that much capacity at a good voltage. The voltage will be lower and the inverter performance will decrease. So we can technically charge to 3 volts and that can give us 30 volts, but most of the capacity will not be at that voltage. It will drop very quickly. So we're just going to have to test it, hook up an inverter and see what happens. I also opened up the other battery pack so we can charge this one up as well. I also noticed that this pack does not have any balancing or BMS mechanism. These are raw cells in series. And you'll notice that these screws right here connect to the balance leads if you actually have a BMS. But because these are used cells, maybe the manufacturer said that they will not sell it with the BMS. I'm not sure. But yeah, we do not have any kind of protection features here. And I guess if these are really cheap, I didn't even check the price of these yet, but if these are super cheap and you get even half the capacity, you could put tons of them in parallel and maybe it might work for your specified application. But for most people, this is not ideal. You have to know what you're getting into when you buy used batteries. After looking on the internet, I found a 10S lithium titanate BMS that you could wire into here, but it's $175. So you'd have to be pretty invested on the cell configuration for your system and have some money laying around if you want to use used cells with the BMS. You could use another cheaper BMS that you can program the low voltage and high voltage cutoff, but yeah, most of these lithium titanate BMSs are not cheap. And another problem with using a 6S or a 12 volt configuration with this pack is you have a main terminal right here for your positive, but for the negative, you have to connect to this bus bar somehow and then ignore all of these other cells over here. So that's just kind of difficult. And look at 1, 2, 3, 4 cells you wouldn't be able to use. So that would just be very wasteful. So I guess we'll try to run it at 24 volts. Something you could do is have a 24 volt charger and solar charge controller to charge these up, and then use the DC to DC step down converter. So it takes the 24 volts and steps it down to like 13.6 volts. So then you could actually run 12 volt appliances or possibly a small inverter. Or you could charge a very small sealed lead acid battery because the discharge rate is really good on even small sealed lead acids. But yeah, lots of ways to configure this. I think if I were to do this and I was trying to be very cheap, I would do the DC to DC to 12 volts so I could actually use a real inverter. And then you wouldn't have any issues. But you would still have to have some kind of cutoff system. And man, that BMS is $175. So, I don't know. This is very difficult to use right here. Something else that I just realized is that on the DALI BMS datasheet for lithium titanate, balancing does not occur until it's at 2.65 volts. And that's 15.9 volts. So if you're trying to use lithium titanate with a 6S BMS from DALI or pretty much anybody else and you cannot program that setting, that means you will not have balancing until your pack's nominal voltage is at 15.9 volts. That means that most people using it with inverters that cut out at 15 volts will never have a balanced pack and it will never trigger it to turn on. So that's really bad. If you're trying to run 12 volt appliances with the BMS, you can say forget it because your packs are going to go out of balance over time and you're going to lose capacity, and then over a long time the longevity will suffer. But what you could do is use an active balancer instead, or a dedicated 6S balancer. But the problem with that is because the lower nominal voltage of each cell is so low, most of those balancers don't work until you're at like 3.6 to 4.1 volts. Or at a very high state of charge for other lithium ion chemistries. I actually tested this in a previous video. So this is kind of difficult. If you want to keep your Titanate packs balanced, it might be very difficult. A 5S pack wouldn't have this problem, but then your voltage is going to be like an 11.9 for most of the time. So I don't know, very difficult to use chemistry, you guys. This is why we use lithium iron phosphate, specifically this reason alone. All right, guys, it's fully charged, so we're going to connect an inverter. So we have the main negative, the main positive, a Hall effect sensor connected to a 24 volt, 3000 watt pure sine wave inverter with max surge of 6000 watts. Because this is a 19 amp hour pack, we should be able to comfortably push 100 amps. I can't believe this little pack is pushing this many amps. That's incredible. So the performance was really bad and the low voltage alarm was beeping like crazy, but we got 18.4 amp hours out of 19 at a very high C rate. So that is really good. These are great cells. The only problem is that the voltage is lower than what I want it to be for this inverter. If this had like 1 or even 2 more extra cells, the performance would be perfect. It'd be flawless. But yeah, very impressive results, you guys. That's 96% of the rated capacity. What is nice about the lower voltage is the inverter will automatically disconnect. So you don't really need a BMS for the low voltage disconnect if your inverter has one at like 20 volts for a 24 volt inverter. So that's impressive. Let's try to push a little bit more power out of this. So we pulled 20.9 amp hours from a battery that's only rated for 19 amp hours. But the BMS is removed, and this is like a raw cell system, and the cells are just connected in series. So what I'm thinking is that the BMS that they removed changes the charge and discharge bandwidth cutoff voltages so that you only get 19 amp hours. But I actually think, because we still have some more voltage left over, but we can't use it because the voltage is too low for this inverter, I think these are 25 amp hour cells. And then they're cycled in a way so you only have a usable capacity of 19 amp hours. And if I could get these cells out, then I could actually weigh them and figure that out. But I contacted Battery Hookup this morning, and they are glued to the bottom of this thing. So it's very difficult to remove them. So I'm not really sure, but they look like the same form factor as our grade B 20 amp hour prismatic cells, but those were already pulling 21 amp hours. And I'm thinking that those were probably originally 25 amp hour cells. So I think all of these are 25 amp hour cells because they're the same shape and size, and they're all pulling past the rated capacity. And just to give you an idea of how bad the lower voltage is, imagine running all of your equipment for 12 volts at like 10 or 11 volts all the time. So this inverter already has a very low voltage cutoff as it is compared to other inverters. So yeah, that's the biggest drawback. Now we're gonna test this battery pack at a lower C rate and try to get past that capacity. Let's try to get 25 amp hours with this one. Well, and this case is pretty warm from that test. Wow. All right, guys, this battery is fully charged, so we're gonna do the low C test now. Guys, just imagine if you dropped a tool in here with all of these battery terminals. Oh my God. These can discharge 10C, so there'd be so much power coming out of this, it would be nuts. All right, guys, same test as before, but at only 20 amps instead. Well, that's a bummer. I can't believe it performed less, but oh man. So this one only pulled 20.3 amp hours at a reduced C rate. That's very strange. But these are used cells, so there's a good chance that these have different capacity ratings, or, you know, one was cycled more than the other. But this is lithium titanate, so the degradation is very minimal, so I don't know what's going on. Let's turn the heater back on. All right, let's see what we got. 21.5 amp hours, guys. But for being used cells, these are very impressive. It's up to you if you guys want to buy these. I'm going to have a link below, but you have to understand what you're getting yourself into. And you have to know how you're going to hook it up and what you plan to do, because it's a little difficult. And I really can't think of an application where I need that high of a C rate, a 10 C rate. This thing would discharge in 10 to 20 minutes. Like, what application would I actually use that for? The fast recharging is great, but like I said, when am I going to need that for solar power? I don't. And lithium titanate does have an amazing charge cycle life, but a big problem that people do not realize is that you still have calendar aging, and that's natural aging inside of the cell. And so over time, even though these are rated for 20,000 charge cycles, and you'll say, oh, that's gonna be in like 50 years or something. The problem, though, is in 20 years, you're going to have natural calendar aging, and I'm not sure what the degradation is like, but all lithium-ion batteries after 20 years are going to have reduced capacity. So, I don't know, and they're very large and heavy. You could easily get a lithium iron phosphate, and it would have a better round-trip efficiency, so you would have to spend less money on solar panels and other things in your systems. So, like I've said before, I'm just not a big fan. I wanted to test these cells, but I already did. And they're grade B cells, and we got 30 amp hours. They do look very cool, though. I mean, come on, look at this thing. Or use these little cells that performed very nicely. You can, but just understand what you guys are getting yourself into. If I were to choose lithium titanate, I would buy grade A Yinglong cells that are rated for 40 amp hours, and then I would buy a dedicated BMS, and I'd probably do a 6S or a 12S. If you do that, you can build an awesome pack. And all of these problems I'm talking about will not occur, except for the balancing problem. All of the BMSs I find for 12 volts, you have to charge it to 15.9 volts till it starts balancing. Maybe you don't need to balance that much with this cell chemistry. Depends on how large your pack is and your C rate and the internal resistance and how the cells drift over time. But you can still build an awesome, LTO cell system. But for solar, as I've always said in the previous videos, I would not use it. There is not much benefit. It is heavy, expensive, inefficient, large. I just do not like hearing those words in my mind. So yeah, I hope you guys liked this video. I felt it was fun to find all these other interesting aspects of lithium titanate, and I will talk to you soon. Alright, I will have links below if you guys want to check out these cells. But yeah, understand what you're getting yourself into. Alright, I'll talk to you guys later. Bye.